So the next step is lithography. So in lithography, we are going to first look at the process of coating, and then how do we transfer the pattern from mask onto the soft photoresist, and later on we will transfer the pattern, right? So let's look at how the lithography bay is organized. What we see now is the lithography bay inside the clean room. So as we discussed during our litho lectures, that lithography bay will have this not the white light but the yellow light, right? The reason for that is the photosensitivity of the photoresist that we use here. You don't want the photoresist to be exposed to the wavelength, lower wavelength that will already expose the wafers, right, before you illuminate using your lithography tool. So the clean room, inside the clean room, the lithography bay will always have this yellow lighting, all right, so that you avoid any sort of exposure to broadband source or the source of the exposure itself, right? And you have all the inspection tools, coating tools, including baking. All those tools are available within the bay, right? So the next step is to coat the wafer. Before coating it, we have to dry the wafer. So the first step is a dehydration bake. So we want to remove any water that is sitting on the wafer using dehydration bake, and that is done using a hot plate. So we place the wafer on the hot plate, which is maintained at around 110 degrees C. So this is slightly above the boiling point of water, so that all the water present in the wafer is evaporated. So after evaporation, so now we have dehydrated wafer, and now the wafer is taken for coating. So the wafer is put on the spinner. So we use spin coating of the photoresist. So we are going to place the wafer centered in the spin coater, and then we have to select the appropriate program, right, to for rotation. And before that, we will coat drop cast photoresist. So you can see here sufficient amount of photoresist is coated on the wafer, and after coating it, we are going to spin it. So once it is there, we are going to spin it, and this spinner will rotate at various RPMs, as we also discussed during the lecture. Initially, it's going to be the spreading phase with the lower RPM, followed by higher RPM to thin it down. So once the coating is done, the wafer is taken out of the chuck, and then we are going to do soft bake. So far the photoresist is in a slightly viscous phase, right? So now we have coated it, we want to solidify. So the solidification happens when you bake the wafer. This is called soft bake. So this can be done at various temperatures, depends on the photoresist material. So once you are done with the soft bake, we are going to do the exposure. So what you see here is a contact or proximity aligner tool, right? So you can see here the tool has various components, right? So the tower that you see here is where the optical source is sitting along with the optics, and there will be some gas control need to be done. So that is where the exhaust is also. So this is the lamp that you see here, and once you have prepared your wafer, now you come to the lithography tool, and in the tool you have to select the right programs to operate the machine. So once you log into the machine, you should have access to the tool in order to do this. So once you have access to the tool, you log into the tool, and then you choose the right, you activate the tool first of all, and then we have to first put the chuck. So what you see here is the holder, the sample holder that's being put in. And this is the mask holder, and the mask holder is held in place by screwing in. So what you see here is the mask plate is being taken out of the mask box, and we try to dust off any loose particles sitting on the mask using nitrogen gun. So a pressurized nitrogen flow, and then we place the mask onto the transfer chuck. And now the mask holder is going to take the mask and it is going to hold the mask in place. Various adjustments are made, as you can see here, by moving the vernier. So now the microscope is brought in to visualize the positioning of the mask. So what you are seeing here in the screen is the mask, right? Whatever features we have in the mask is being visualized using the microscope that we have. The operator is trying to find the alignment markers. So the crosses are the alignment markers, which is important to align the mask. So we should first align the mask. So the mask could have either translational or rotational misalignment. So we are trying to make the mask held in place without any alignment errors. So on the right side of the screen, you can see here the position of X and Y, both on the left side and the right side. So these dots signify where the alignment markers are, and they should be exactly in the same location. So once the alignment is done, then we can place the wafer now. So the wafer is positioned on the wafer chuck, and then it is inserted inside so that it aligns on top of the mask. So you can see here the objective is trying to focus onto the mask here. So you'll see on the left you're getting into focus. So what you see here bright is the mask, right? And on the right side also you will slowly now see the structures are going to get into focus. And you can see here the vertical distance between the wafer and your objective, right? So left side and right side. So both left side and right side is in focus now. And what you see in the background, this is on the wafer, right? So these are all the alignment marks on the wafer, and this is the alignment mark on the mask. So now we have to align these two. So this is how you achieve alignment between the structure that is already present on the mask and the structure you have on the mask. Okay, so between the wafer and the mask, we have to do this alignment by using this alignment structure. So we are trying to move the wafer, both translational and rotational. So you can see here now we are aligning both left side and right side, trying to get minimal misalignment between the two layers, the layer that is already present and the layer that we are going to project. And once the alignment is done, we are going to expose the wafer. So fine alignment is done now. So the operator is checking if the alignment is good on the different sides. So it is important to check alignment across the structures that we have, not just at the one alignment marker. We should also look at the different corners and where do you think there could be some critical structures. So you try to make sure that the alignment is done properly, right? So that you can avoid misalignments. You might spend a little bit more time on this alignment, but at the end you will get a very good reproduction or overlay from doing so. So now the microscopes are retrieved and we are going to expose. So now you can see here a blue light appearing. So this means we are exposing the wafer, and once the exposure is done, the exposure head is retrieved, right? And after the exposure, the wafer is retrieved from the wafer chuck. So now you can see the mask lifted up. Initially it was in contact. Now we have retrieved the mask and the wafer is out. So this is how an exposed mask, exposed wafer would look like. And now we have to develop. So once you put the wafer into the developer, you will slowly start seeing the features coming out. And after developing it for the required amount of time, then we have to rinse it with water, right? So we are arresting further development by putting into deionized water. So after rinsing it, removing all the developer, now we have to blow dry it. So that means we are going to blow nitrogen on top of the wafer and remove all the water that is present on the wafer surface. So once the drying is done using gun, then we have to inspect the wafer. So whatever structures we have, we should inspect whether they have been reproduced properly or not. So if you remember in the earlier section, we saw the GDS file or the design file that had these sort of cantilevers. So what you see here are those cantilevers, so now reproduced on the wafer surface. So what you see here the blue, right, this is now the silicon nitride, and the lighter structure here, right, the lighter shade, this is the photoresist, right, the photoresist of the pattern that we designed, right. So this is the cantilever we would like to transfer the pattern to. So we are looking at whether there are any defects present on the mask or not, right, reproduced structure. So after inspection, we do post exposure bake, right, or hard bake. So what we are trying to do here is to remove all the hydrants or water that was present on the wafer. So we are done with the lithography now. So as we saw from the top down images, we had the structure, right, so where we had silicon nitride, and then this is your photoresist, right. So this is your photoresist that is sitting on top of the wafer, and now we have to transfer this photoresist into silicon nitride, okay. And the first step here is to anisotropically etch this nitride, right, And in order to make this cantilever, we have to remove the underlying silicon substrate, right? So the silicon nitride etch is going to be done in ICP RIE tool. And then the next step is removing the underlying silicon, right? So which should be done in an isotropic manner. That means you want to remove all the silicon nitride that is present underneath. So you don't want a directional isotropic etch. So here we want isotropic etch, right? So how do we do this? Also by using dry etch, we will use a different chemistry, right? SF6 chemistry, in order to remove the underlying silicon using isotropic process. And once this is done, we can have these cantilevers that are freestanding. But it is not done yet because we have photoresist still present, right? We have to remove this photoresist. And the photoresist removal is also done using wet process. So we can use oxygen plasma in order to remove the photoresist. So on a whole, all the three processes can be done using a single tool. In fact, we can sequence this so that all these three processes can be done in one go, right? So that is what we are going to do in the next process. What we see here is a ICP RIE reactor, which we are going to use to etch silicon nitride anisotropically and isotropic etch of silicon, and then removal of photoresist. The moment you see this tool, you can clearly identify this should be a ICP reactor, that is inductively coupled plasma. Because you can see here on top of the tool, you will always see a dome, right? So this transformer is what generates high density plasma, right? We saw in the dry etch lecture that you have a coil here, a transformer coil that is going to generate the plasma, and the wafer is going to sit at the bottom. So let's see how we are going to use this tool. So the tool is operated using a software here. And the first thing is to load the wafer inside. So this is the load lock. And we are going to place the wafer that we want to etch right in place of the transfer robot arm. And then we will pressurize the chamber. And now the wafer is pushed. So once the loading is done, we have to select the right recipe to etch the nitride. So what you see here is a nitride etch recipe where we have various gases that are present, and we are going to run that particular recipe. And you can see here there are various gases that are present, right, in the system, and we have chosen a certain gas that we have to flow through. And we have to maintain the right time for that particular etch, and also the pressure, required pressure that is required to do the etch. So once we achieve the right pressure and gas combination, what you see here is the flash of the plasma. So here what is happening is the first step of the etch process, where we are trying to etch anisotropically silicon nitride. So you can see this nice color coming out of the plasma because of emission that we saw in the dry etch. So the emission comes from the various gas molecules that are excited, and when they are coming to the ground state, they emit photon, right? In addition to all the other processes that we have, this emission process is the one that is giving us this nice glow, right? So and this is the first step in this whole etch process. And now the flash is gone, we are moving to the second step. And in this step, we are etching silicon, the underlying silicon, where we are doing an isotropic etch of silicon using fluorine chemistry. And once this is done, again the flash would go down, and now it comes back. So in this case we are etching photoresist, right? So we are removing photoresist by using oxygen plasma, and the oxygen plasma cleans up all the residues that you have on top of your wafer, and now the cantilever is clearly made without any photoresist, right? So after this process you have a clean wafer now. And once the process is done, we are going to retrieve the wafer out. So the robot arm goes in and it brings the wafer out. And now what we see here is an etched wafer. So you can see here these cantilevers are present here, and this is the silicon nitride part, right? So the dark region that you see is silicon nitride, and this light region that you see, this is silicon actually. So we are removed this nitride and removed silicon as well in order to create an undercut, so that we create a cantilever, a freestanding cantilever. So once we have this wafer, we are going to take this for inspection. So again we are putting this under a microscope, and what you see on the screen, so these are all the cantilevers, right? So now these cantilevers are in silicon. So initially during the inspection we saw similar kind of image, but during that point of time the cantilevers were defined on the photoresist. So now all these structures are in silicon. So there are cantilevers of various shapes and size. So we are slowly trying to zoom in and then see the quality of this cantilever being fabricated. So what you see here is one of the cantilever group. So the blue again, so this is the tint that you get because you have silicon underneath. So the whole region has silicon nitride. The blue region has silicon underneath, while this part, right? So this part has no silicon underneath. So the light color that you see is nothing but the silicon nitride cantilever, and then you can nicely see this the isotropic edge feature really looking like sharp, right? So if we zoom in, we can nicely see those features, and the inspection is done in order to measure what is the width and length of these features, which is very important during fabrication. So what you see here is a very fine isotropic feature, right? So normally in a isotropic edge you don't get sharp corners, right? So this corner will be made into a curve like this. That is what we see here as well. We are redoing the measurement. So the length of the cantilever is also measured here, which is 132.8 micrometer in this case. So this is a very interesting image what you see here. So this part is silicon nitride, and what you see here, this blue part, this is where the silicon is still there. So silicon is holding the silicon nitride beam. This is the fixed part of the cantilever beam. and here you can see the nitride beam. So you can see the feature is nicely focused in this part. Here it is not focused well enough. The reason for that is this cantilever is not flat, right? So because of a slight stress in the film, so you don't get a very flat structure, and that is the reason this part is out of focus because of curling effect, and this part is in focus. In this shorter cantilever, you see the whole of the cantilever is in focus. The reason for that is the curling is not very aggressive because it is a shorter cantilever, and that's the reason why you are able to focus the whole length of the cantilever here. And we are also going to measure the step height, right? We only saw from top down how the image looked like, and now we are going to do step height. Because we have etched the film and also we have created an under etch, you expect a large step height difference in the wafer. So we are putting it for step height measurement. So here we are going to use a stylus which is going to go over the structure and measure the height. So we are going to put the stylus on top of this structure, and you can see here the stylus is slowly moving, right? So it's moving upwards, and then you can see the trace here, right? So the trace is moving, and keep a close watch. Once it reaches the edge, there will be a change in this. See? So there is a change in the thickness, as you can see here, a sudden change in the thickness that we see. And this thickness change is because we have etched this film, right? So we have to do some baseline correction. So it is tilted. So once you do the baseline correction, we'll see the height difference that we get. So from the left side to the right side, if you can see here, the topography is about 10.291 micrometers. So we have etched 200 nanometer, approximately 200 nanometers of nitride, and we have etched nearly 10 microns of silicon. So after all this process, so this is what we have been measuring. So what we measured was this height, right? And this height was 10.291 micrometers, right? And this is a demonstration of how we fabricate this cantilever. Just to give you an idea, this is an scanning electron microscope image, an SEM image of the cantilever that we just saw. So these are all the cantilevers. This is nothing but the silicon nitride cantilevers, right? As I mentioned, the long cantilever, it is not flat, right? It is not flat, and that is the reason why you are unable to focus across the length, while the shorter ones are really flat. So we were able to focus it, and we can see here nicely the isotropic nature, right? So you can clearly see, because of isotropic nature of the silicon edge, you see this nice curved edge, right? And you can see something like a shadow here. The reason for that is the etch rate difference, right? So we had this cantilever, and then you are etching from both the sides, right? So you will always see a etch height difference between the edge and the center, because the edges are first etched compared to the center. So the height difference, or the thickness difference, will always exist there, and that is the reason why you see this sort of shadow here, right? And with this demonstration, we have come to an end of this whole demonstration of fabricating a silicon nitride cantilever using various unit processes that we studied in this course, right? So This is all done using clean room tools at Center for Nanoscience and Engineering, NNFC in particular. So all the process requires meticulous planning, right? And also following all the procedures within that unit process. What is the gas that you have to use, how much gas you have to use, and what is the pressure and how much time is required. We need to control all of this. Most of this thing comes as a software attachment to these tools that you can control, but nonetheless we should be very careful about the recipes that we build. For some of you who might have never seen a clean room, I hope you got an idea about how things are done inside the clean room and how these tools work and what are all the procedures one need to follow in order to achieve the desired device that you want.